Welcome, everyone. Today's the first talk of the year is by Sushant Sachdeva. Before getting there, let me again remind everyone, also those watching on YouTube, that we are always looking for more ideas, for more recommendations for talks. So if there's something you want to hear about, let us know. Also, I should say that the next talk in 2 weeks will be by Swastik Koparty from Rutgers. So I hope you also all join us there. So I think we're essentially ready to start. We're still waiting for a couple of more groups, but we can start while they set up. So today's talk is by Sushant. Sushant graduated from Princeton in 2013 under the supervision of Sanjeev Arora. He spent postdoc at the Simons Institute and then 2 years at Yale with Daniel Spielman. Currently, he's a research scientist in Google. His interests are in his research interests are in algorithms, optimization, and machine learning. Without further ado, I'll hand over the mic to Sushant, who will tell us about approximate Gaussian elimination. And again, we encourage questions. So welcome, Sushant.
Thank you. Well, thanks all for coming. And thanks to Oded and the other TCS Plus organizers for giving me this chance to speak here. And definitely, we should have time for questions. So please just unmute yourself and ask a question.
Actually,
Great.
One thing, Sushant, interrupting, one thing I forgot to say, we usually go around the table and kind of introduce the audience.
Oh, the audience,
I want to do it today because I thought we have too many people, but let's maybe quickly do it.
Sure.
Also, let's give a chance to other groups, for other groups to join. So definitely. we have Amit from Waterloo. Let's see if you can, here.
Yes,
I can. Hello, everyone there. I see a big group. We have Leo joining from USC with the group there. Hi, guys. We have Madhur with the group from TTI, Chicago. Hi, guys. Piyush with the group from Caltech. Hi, guys. Sharvas, who is now no longer, is currently not in NYU, is actually in CWI in Amsterdam. Hi, guys. Good to see you all there in Amsterdam, despite the late hour. We have Sina, who is joining us from University of Michigan. And we have Sorachai, who is joining us from Michigan State University. Okay. So, and that's it for now. So back to you, Sushant. Sorry for the interruption.
Great. No, that's all right. Excellent. So great. So let's begin. So we'll be speaking about approximate Gaussian elimination for Laplacians, and this is joint work with Rasmus King, who's a graduate student at Yale. Great. So let me first quickly give you a summary what we'll be speaking about. So we'll talk about solving systems of linear equations, AX equal to B, where say A is a given n by n symmetric matrix, B is a given n-dimensional vector, and you would like to find X such that AX equal to B, right? And in case A is a Laplacian, we'll call it a Laplacian linear system. So solving such systems is a fundamental primitive in a lot of applications. And even though we know how to solve such general systems in polynomial time, for solving large systems, that's not good enough, and we would like much faster algorithms. And in a breakthrough work for Laplacian linear systems, Spielman and Teng showed that we can actually solve them in nearly linear time. And this work has been extremely influential in the design of fast algorithms and was as such recognized with the Gödel Prize last year. So if you've seen the original paper, if you haven't, I encourage you to go see it. You know it's over 100 pages long, and today is a sum of 3 journal papers. But today, I'll present to you an extremely simple, nearly linear time algorithm for solving these systems, and essentially give you the entire proof in this talk. Good. So we'll show a nearly linear time solver for Laplacian systems based on sparse approximate Gaussian elimination. And we'll define everything that we talk about here. Right? And this paper will be appearing at the upcoming Fox. Great. So this result does generalize actually to a larger class of linear systems, but we won't speak of that today. I'll only focus on Laplacian linear systems. So I will define every single thing we need, even a lot of preliminaries that most of you would have probably seen, but I'll go through them a little quickly so that we are all on the same page. So let's first really define what are Laplacians. Right? So a Laplacian is a symmetric n by n matrix that's associated with a weighted undirected graph G. Let's say the graph G has n vertices, m edges, and weights denoted by W. So to define the Laplacian for G, before that, let me first just define the Laplacian for a single edge 1, 2. So for an edge 1, 2, the Laplacian is shown here as L. It has a 1 on the 1 diagonal, a 1 on the second 2, 2 diagonal, and -1 on the 1, 2 off diagonals. A more intuitive way actually to think about these Laplacians is in terms of their quadratic form. So for any vector x, the quadratic form x transpose Lx for the single edge Laplacian is exactly x1 minus x2 the whole square, where x1 and x2 are the first and the second coordinates of the vector. Right? Now, this quadratic form allows us to easily define a general Laplacian. So for the graph G, the quadratic form of the Laplacian is given as the following. So it's a sum over edges uv, the weight of the edge uv, times xu minus xv the whole square. Right? This is the quadratic form of the Laplacian. Now just rewriting this as our matrix, we can write the Laplacian for the graph as a sum over edges uv, weight of the edge uv, times the Laplacian of the edge uv, which is just 1 on the UU diagonal, VV diagonal, and -1s on the off diagonals. All the other entries in the Laplacian for UV are 0. Good, so that's the definition of Laplacians, which I guess a lot of you might have seen. A lot of you might have actually seen a different definition, which is just the a diagonal matrix with the degrees on the diagonal minus the weighted adjacency matrix. These two are actually equivalent definitions for Laplacians. Right? And we'll be solving systems in Laplacians today. Good, so but why do we care about solving these systems? So this problem actually originated in scientific computing particularly for applications for solving partial differential equations via finite element method. But since then, it has found its way into a lot of applications in algorithms and theoretical computer science. And today it's used for optimization on graphs, for learning on graphs, for a lot of faster flow algorithms, for graph partitioning and so on. So really a huge range of fast algorithms use Laplacian solvers. And that's why there's a tremendous amount of interest. So how do we go about solving them? So if you were to solve them naively, say by using the college method of Gaussian elimination, it would run into time n cubed. And this would be n cubed time even if the original matrix is sparse. Now you could use theoretically faster matrix multiplication algorithms to get you down to n to the omega, where omega is roughly 2 to the 0.37, which is the matrix multiplication constant. Now, as I said, Spielman and Teng showed that we can solve Laplacian linear systems in time nearly linear in the sparsity of the Laplacian. So, and since then, there has been a large number of works trying to build better and faster solvers. In fact, the fastest solver today, due to Cohen et al., says that Laplacian linear systems can be solved in nearly m root log n time, where m is your number of edges in the graph, which is basically the sparsity of our Laplacian. Then this is essentially even faster than sorting the edge weights that have been given to us, right? And that's kind of surprising. Great, so that's why we care about them. Now, in order to tell you more about what it means to actually solve these systems, so we'll not solve them exactly, we'll solve them approximately. To tell you more about that, let me quickly review some basic notions about PST matrices. So a PST matrix, or a positive semi-definite matrix, is a matrix A that's symmetric And for all vectors x, we have x transpose Ax is greater than or equal to 0, non-negative, right? And Laplacians are PST just because of the way we define them by their quadratic form, right? The quadratic form was the sum of squares, which is always non-negative. Good. So a PST matrix naturally defines a norm. So the A norm of a vector x is just the square root of the quadratic form x transpose Ax. And when we say we are going to solve a system Lx equal to b approximately, that means that we'll find an x tilde such that x tilde is close to the correct solution x, and it's close in the Laplacian norm, L norm. So we say that x tilde is a delta approximation solution if x tilde minus x in the L norm is at most delta times the L norm of x. So if you've never seen this Laplacian norm or the matrix norm before, it probably seems a little ad hoc and strange to you, but actually it turns out that this is the right norm for most applications. And this is also the norm which is the right norm for approximation in the applications that require them, and it's also the right norm in which most solvers will give you solutions for, right? In particular, our solvers will give us solutions in the matrix norm. So more formally, we'll show that we can find a delta approximate solution to a Laplacian system in roughly m log cubed n time and log 1 over delta. Right? So this will be our formal theorem of the Laplacian solver. Good. So how will we go about this? We'll go about these by approximating our Laplacian system.
Sushant?
Yes.
That's a small question.
Yes.
If I don't care about log factors, I could take delta to be very small, like 1 over n cube. Is it true that in this case the norm is,
yeah, it's basically the same.
The same norm, right? Because it's not relatively well conditioned, right?
Right. So okay. So let's say the graph has polynomially bounded weights. Mm-hmm. If you have polynomially bounded weights, then the condition number of the Laplacian, the largest eigenvalue by the smallest non-zero eigenvalue, is again bounded by polynomial. And you can lose that polynomial in the delta and translate to, let's say, the L2 norm.
Okay, thanks.
Right. So that just adds another log n. Great. So, okay, excellent. So we'll want to approximate these systems. So let's first ask, what does it mean to actually approximate these systems? So we defined positive semi-definite matrices. The way we'll actually write them is to say that 0 curly less than or equal to A means that A is a positive semi-definite matrix. And this is actually a partial order. So A curly less than or equal to B is equivalent to saying that B minus A is positive semi-definite. Right? And this allows us to present a notion of approximation for PST matrices. So we say that a matrix A, epsilon approximates a matrix B if A is curly less than 1 plus epsilon B and B is curly less than 1 plus epsilon A. Right? So both matrices are within 1 plus epsilon of each other. So the way to think about, so I know most of you have seen this notion before, but if you haven't, it's really an interesting sort of notion. So it's not a notion that says that you must be entry-wise approximate. It's not a notion that says that your eigenvectors are equal and your eigenvalues are within 1 plus epsilon. So the right way to think about it is that each PSD matrix actually identifies an ellipsoid, which is given by exactly the set of vectors such that x transpose Ax is exactly equal to 1. So it's the level set of the quadratic form. So if you look at these level sets for A and B, they are such that these two level sets need not be axis aligned, but they are such that in any direction, the two level sets are at most 1 plus epsilon apart. Right? And that's the right notion for approximating PST matrices. And if you actually have a good approximation, you can use it to solve linear systems. How? So if you want to solve Ax equal to B, and if somebody gave us for free a B that approximates A, say up to a constant half, and B is easy to invert, then we can actually solve the auxiliary system B inverse Ax equal to B inverse B. It's an equivalent system. And now this can be solved by a simple iterative computation. So you start with an initial guess for x, let's say all zeros, x0, and then you update it according to the following rule. Xi plus 1 is the new guess is equal to the old guess xi minus a constant times b inverse, which we know we can compute quickly, times the residual of the system, which is a times your current guess xi minus b. Right? And it's really a homework problem that if you apply, starting from all zeros, if you apply this iteration roughly log 1 over delta times, then you'll actually achieve a delta approximate solution. Right? And the approximation factor, which I've picked as half here, that disappears into a constant dependence in the number of terms. So if you had a t approximation, you would have a linear in t dependence on the number of iterations you need to take. Right? So now it suffices for us to actually find a good approximation to the Laplacian matrix. Great. And how will we do that? We'll do that via Gaussian elimination, and really the symmetric version of Gaussian elimination, which is called Cholesky factorization. Let's really first start with defining what is Cholesky factorization. So it's really a classical concept in linear algebra, and it says the following: that for any PST matrix, for us it's a Laplacian L, there exists an upper triangular matrix U such that U transpose U is exactly equal to the matrix. Okay, and why is Cholesky factorization useful for solving linear systems? That's because now I can exactly write that my solution X, which is L inverse B, is exactly U inverse U transpose inverse B. But since both of these are triangular matrices, the inverses are really easy to apply. Right? And what we will work with actually is an approximate Cholesky factorization, where we'll find an upper triangular matrix U so that U transpose U is approximately L. Now again, these being triangular matrices, they are easy to invert. And now combining it with iterative refinement, this means that we'll be able to find an delta approximate solution in log 1 over delta steps of iterative refinement. Right? So so here's my claim, and if we have a concern, we should ask a question. Here's a claim that if I give you for free an upper triangular matrix U such that U transpose U is approximately equal to the Laplacian, then we basically have a fast linear solver, because we can invert these matrices fast, and we can apply it log 1 over delta times, and we would be done.
Sushant, is it also true for sparse matrices? Because use.
Okay, good question. So actually, I should have said that. So okay, so for exact Cholesky factorization, let's go back a slide. Even if L is sparse, there are matrices, in particular Laplacians of expanders, that require U to be dense, even quadratic dense. So that's too costly. But if U was sparse, and even if it's approximate, then we'll be in good shape. And that's actually exactly what we will show.
You're saying because you're dealing with the approximate case, you can find a U that's sparse, assuming L is sparse.
Yes.
And then what about U inverse?
Good. So U inverse need not be sparse, but it's still cheap to apply. That's the key difference. You may not be able to explicitly write U inverse quickly, but computing U inverse B for a vector B is linear in the sparsity of U. Right. So is the approach clear? Please, it's a good point to ask questions if this is not.
History-wise, was that already known to Speedman and Tang, or is this?
Okay, no. This was only known in in the last paper that we wrote, this was Pengs, Lee, Spielman, myself, and Rasmus. So the 5 of us. So it was not known for a very long time that you can actually write these sparse approximate Cholesky factorization. Good. So here's the formal theorem we'll prove. We'll prove that for any Laplacian L, in nearly linear time, we can compute an upper triangular matrix U so that U transpose U is approximately the Laplacian and U is sparse, right? Both the sparsity and running time are roughly m log cubed n, where m is the number of edges. Good. Now that it's sparse, this implies a fast linear solver, right? Why? We will use U transpose U to do iterative refinement, and each step of iterative refinement is cheap because U is sparse. So since it's sparse, it's and triangular, its inverse is easy to apply. Good. And in particular, this immediately implies an m log cubed n log 1 over delta Laplacian solver. Excellent. So how do we go about finding such an approximate Cholesky factorization? So some of you might be familiar with Cholesky factorization. If you are, I would like you to forget your familiarity and just think of it again. So because I'm going to present an additive view of Cholesky factorization, whereas the standard view in textbooks is multiplicative, where you write a matrix as a product of 3 matrices at every step, and then you multiply the matrices. So you should forget that view. I'm going to present an additive view. Why? Because that view will be very easy for us to apply concentrations for sums of random matrices. Okay, so let's first do exact Cholesky factorization. So our goal is to find an upper triangular matrix U such that U transpose U is equal to a given matrix, a given PST matrix A. And I'll run that example with the help of this matrix given here. I'll show you the algorithm with the help of this example. Good. So we have a given PST matrix A. Now, here's the first step. We'll find a rank 1 matrix that agrees with A on the first row and column. Right? So A is symmetric. There's a unique rank 1 matrix that agrees with A on the first row and column. We compute this rank 1 matrix and then we subtract it out from the original matrix. Okay? And once you subtract it out, immediately the first row and the first column in the difference is 0. And we call this eliminating the first variable. This really corresponds to what you do when you do Gaussian elimination in the first variable. You eliminate, you get rid of the first row and then use that to get rid of the first variable in all the remaining equations. This exactly corresponds to that operation. Now, here's a key property of Cholesky factorization, that if you started with a PST matrix, the remaining matrix is actually PST. Okay, so now that it's PST, I can repeat this procedure. I can find a rank 1 matrix that now agrees with the matrix on the next row and column, on the second row and column. And you subtract out this rank 1 matrix, and we've now zeroed out the second row and column. And so on, we can repeat. Right? So we repeat until we have written our original matrix exactly as a sum of rank 1 terms. And these rank 1 terms have very special structure. The second vector has a 0 on the first coordinate. The third vector has a 0 on the first and the second coordinate, and so on. Right? And now this allows us that we can stack all of these vectors together, exactly the vectors that constitute the rank 1 terms, to obtain a U transpose U factorization. You see the matrix on the right, I've just stacked those vectors in as rows of the matrix. Right? And this is exact Cholesky factorization.
There's a question.
Yes.
Kaltek? Can't really hear you guys, even though you're not muted.
Pish, yeah, we can't hear you. Maybe you can.
Yeah, don't be shy. Okay. It must be something wrong with the microphone. So you can type.
Yeah, or you can type the question if that's easier. Okay. Why does the matrix remain PhD? Okay, good. So it's not an obvious fact, and it requires proof. But it is a standard and important property of Cholesky factorization that you can actually that the remaining matrix still remains PhD. But actually for Laplacians it's a lot easier. I will show it to you for Laplacians essentially, and there it's a lot easier to see. So let's see that what in a few slides. Piyush, is that okay? In a few slides I'll show you why it's true for the Laplacian, and that's all we'll care about today. Okay, so in this whole procedure, what was a running time? So a running time was proportional to the sums of squares of numbers of non-zeros in these vectors. Why is that? That's because, say, the first time you create this rank 1 term, the number of, let's say the vector had k non-zeros, then the number of non-zeros in the rank 1 term is actually k squared. Right? And you need to subtract out this rank 1 term from the original matrix. So that contributes a square in the number of non-zeros in the first one, and so on. Right? So a running time is the sum of squares of numbers of non-zeros in these vectors. And this, in the worst case, can be n cubed even if our original matrix is sparse. Okay, so let's see, what does Cholesky factorization mean on Laplacian and why is it special there? Right, we'll only care about Laplacians in the talk today. So first let's interpret Cholesky factorization in terms of our graphs that define the Laplacians. So one key fact here is that in fact the remaining matrix is always Laplacian. Okay, so more precisely, here is a Laplacian as an example for a Laplacian for a star, and so it's a star centered at the first vertex. Now we take the star and we write it as a rank 1 term on the left and the remaining term on the right. The remaining term is exactly a new Laplacian. And we can actually interpret this in terms of graphs. So if here is a graph corresponding to the original Laplacian, and we are eliminating a vertex v, then eliminating the vertex v corresponds to looking at all the edges adjacent on that vertex and deleting them, and instead adding a clique onto your neighbors. Okay, and here particularly in the setting of Laplacians, actually it's fairly easy to see that you actually get a new Laplacian and hence it's PSD. Why is that? That's because so for every edge ij, now you get an off diagonal -1 that you're off diagonal 1 that you're subtracting out. That gives you the -1 term. The only thing that remains to prove is that you actually have enough on the diagonal term to actually interpret it as a Laplacian, right? And that's because, so in this particular case, for example, say v, let's say these were all edges with weight 1. Then when you actually eliminate, you will get this clique where each of these edges have weight 1/4. And when they have weights 1/4, then when you subtract them out, you will still be left with terms on the diagonal.
Just to make sure I get it right.
That was not clear. Yes, go ahead.
The rank 1 matrix, right? Yes. So it has, in the case of a Laplacian, assume it's unweighted, say. So in the case of the Laplacian, I would have -1s in the first row and the first column, except the diagonal entry. Right. But then the thing I'm subtracting would have 1s.
So so let's create the rank 1 matrix in this case, right? Okay, so what does the first row and column look like? It looks like 4 on the diagonal and -1s on the off diagonals. So now if we complete this into an into a rank 1 matrix, then the terms we create will actually be will be 1/4. Right?
A positive one when you're subtracting that.
Positive 1/4. So the rank 1 term will have positive 1/4 terms. And when we subtract it out, they will become edges of weight 1/4. And since the question only is what is the row sum, the row sum is basically 0, right? Because 1/4, you have 4 terms of 1/4 and -1, and that in particular means the new matrix after subtraction also has row sum zeros and off diagonals as non-negative. Off diagonals are non-positive, so it's still a Laplacian. Piyush, does that make sense? Okay, I guess I can't really hear you, but okay. So really, if I'm sorry, I maybe should have prepared a slide on that as to why it's a Laplacian. But it's really, but for Laplacians, eliminating a vertex gives you back a Laplacian, and it's really a 2-line exercise. And if you try out this example, it will show you that. Okay, so here's the key interpretation to remember, that when you eliminate a vertex V, the process of elimination removes the edges incident on V and instead adds a clique on the neighbors of V. Okay, and this is in particular the reason for why Cholesky factorization quickly, like the running time quickly blows up. So when you remove D edges, you actually add D squared edges on the remaining graph. And in particular, even if you started with a constant degree graph, your degree starts blowing up. And very quickly, you can add up to roughly n cubed time. And you can prove in particular actually that for expanders, there is no sequence of elimination that does less than n cubed time. Okay, and here's our key insight. The key insight is that, coming from graph approximation, is that we actually don't need to add these entire cliques. We can sparsify them. All we need to do is that we can add a few of these edges and hope to achieve an approximation to our Laplacian. And this will be our approach. Okay, so now let me get to really defining our algorithm. For that, for contrast, let's first quickly summarize what is Cholesky factorization. Okay, so here's Cholesky factorization. I've already said this, but I'm now summarizing what is Cholesky factorization. We pick a vertex V to eliminate. And once you eliminate this vertex, we add a clique on the neighbors of V. And then we repeat. This is Cholesky factorization on Laplacians. Good. And here's our algorithm, a sparsified version of Cholesky factorization. We pick a uniformly random vertex V to eliminate. We sample the clique that would be added by eliminating V. And then we repeat. Okay, so at every step, instead of adding the whole clique on the neighbors of V, we will sample a few of those edges, and then we'll repeat the procedure. And it turns out actually this is similar to a heuristic called incomplete Cholesky factorization that was popular in the 80s for solving these systems. It's not exactly, but similar enough in case you're familiar with that literature. Okay, so and what's our hope for the running time? So for Cholesky factorization, I said that a running time was sums of squares of the number of non-zeros, and that can quickly add up to n cubed. For us, the hope would be that you actually only add nearly, like roughly degree number of edges. Right? Instead of adding degree square, you roughly add degree number of edges, and And as you go on, your average degree does not increase, and hence they add up to roughly near linear in the size of the original graph. Right? That's our hope, and we'll show you how to realize this. Okay, so here's a key step I've not specified in my algorithm, is how do we sample these cliques, right? That's the main step, right? Otherwise, the algorithm is the same as Cholesky factorization. You pick a vertex, you eliminate it, and you go on. And the key step is when you eliminate a vertex, how do you sample the resulting clique on its neighbors? So here's how we do it. So we'll go over, so I'm going to show you how to eliminate the vertex 1 here in this example. So we'll go over the edges of 1. So let's say for an edge, for each edge 1 to v, we'll pick an edge, another edge incident on 1 to u, with probability proportional to the weight of the edge. Okay, and then we'll insert a reweighted edge uv. Okay, so for 1 2, we sample the edge 1 4 and we add an edge 2 4. For 1 3, we sample the edge 1 4, we add an edge 3 4, and so on for each of the edges incident, and then that gives us a sample of the clique, a specified version of the clique. Okay, is the sampling procedure clear? And having specified the sampling procedure, I've specified the algorithm entirely. It's an entirely different question whether any of this actually works, but I hope the algorithm is clear. Good. So let's really ask, how do we go about analyzing this algorithm? And to analyze it, to really set up the whole framework, let's quickly first just ask, what is the matrix we output in expectation? Right? It's the easiest question we can ask about our algorithm. So for that, just consider eliminating the first variable. So what did that correspond to? We said that, so right now I'm just thinking of eliminating the first variable in exact Cholesky factorization. Okay, so in exact Cholesky factorization, we said that you take the original Laplacian, you write it as a rank 1 term plus a remaining matrix, and the remaining matrix in Laplacians corresponds to the remaining graph that was not incident on the first variable, plus a clique that you add on the neighbors of the first variable. Right? And for our algorithm, we said that we'll actually take this clique and we'll sparsify it. We'll draw random samples from this clique. So and let me call this L1. Say L1 is intended to be an approximation for the original matrix L0, original Laplacian L0. Right? And what's the expectation of L1? So in expectation, the rank 1 term does not depend on the choice of sampling. So it only depends on the expectation of the clique that you sample, of the sparsified version of the clique that we sample. So if this was exactly equal to the exact clique that we were expecting to see, then in expectation, the first approximation will be exactly equal to the original matrix L0. Right? And we can continue this across our steps. So here's our key. So our algorithm basically maintains an approximation to the Laplacian after I eliminations. And right? And if at each step we ensure that when we draw samples from the clique, in expectation, those samples look like exactly the clique, then we will preserve the fact that in expectation, our approximations of the Laplacian look exactly like the original Laplacian. Okay, so preserving the expectations is easy for us, and how will we achieve that? So suppose there was an edge E we were about to sample. Its original weight was WE, and instead we are going to sample and include it with probability PE. Now, when you actually include it, if I include it with weight WE upon WE divided by PE, then in expectation, I will preserve the weight of the edge. Right? And this simple scaling up by 1 over the probability of sampling will ensure that in expectation, the matrix we output looks exactly like the original Laplacian. Right? Any questions so far?
There's also the issue of scrambling the vertices, but you ignore it, and for now we don't need to worry about it yet.
So that doesn't that doesn't cause trouble in the expectation actually. So it causes trouble in thinking about it and imagining where the expectation will go, but you can think of it as the following. So choose a vertex first, and then look at sampling the clique that would result from its elimination. And if I ensure that when I sample that clique in expectation, we are right when sampling the clique, that will ensure that in expectation we are right all throughout.
I guess the question is that at some point you're going to use it, and it's not yet here, right?
Yes, no, it's not in the expectation. It will come out when we want to bound the variance of our samplings. Yes, I think we have another question here. Yes.
Let me see.
Yeah, I can hear you now.
Is this just creating like a martingale sequence of matrices at the end of the day, or?
You're breaking off. Make sure you don't hold Control D. Just press it once, and now you're good. I think. Try again.
Oh, okay. Yeah, I was just wondering, are we creating like a martingale sequence of matrices?
Excellent. Exactly. Okay. Exactly. Okay. That's
okay.
In fact, that is my next slide. So once you ensure that the sampling probabilities and our expectations are exactly equal, we achieve exactly a matrix martingale. Good. So I do want to make one small difference, is that so in a matrix martingale, I want to define what are our observations. So I'd initially said Li is a matrix approximation after I eliminations, but we are actually going to consider every edge samplings as a new observation. So every time you're going to sample an edge, that's going to be a new observation of the martingale. Good. So okay, and all our goal is to show now is that our martingale is actually concentrated around our expectation. Okay, and here are two typical requirements for proving concentration. You want to show that every difference has small norm, and the second thing you need to show is that you have low total variance in the martingale. Okay, and this will allow us to prove that the matrix you output, and in particular the approximate Cholesky factorization we output, is approximately equal to the Laplacian with high probability. Good. So how do we go about it? Here I need to first define a little more precisely what will be our martingale. So here's a small concern, is that matrix concentration typically allows you to prove that your martingale Ln looks like the expectation, which is the original Laplacian L, up to epsilon times the identity. But what we really want to prove is that our martingale looks like the expectation up to epsilon times our original Laplacian. Right? So for that, we can just place our matrices in a normalized form or in an isotropic form, and we'll rephrase our goal as the following. So you multiply by L to the minus half on both sides, and you get L to the minus half, Ln minus L, L to the minus half is at most epsilon times identity. Right? And to make this a little cleaner, I will define variables in isotropic position. So these are matrix variables. and I'll denote them in red. So red x is equal to L minus half x L minus half. And throughout the rest of my slides, red variables are variables in isotropic position. This will really clean up our maths. Okay, so here's our goal now. We wish to show that a martingale ln in the normalized like once you normalize them, it looks like exactly your expectation up to epsilon times identity. Okay, and for that, let me first define what are our samples. So for that, recall that the Laplacian of an edge uv was a matrix with ones on the u and v diagonal and minus ones on the uv off diagonals. So at every sampling, so I said our martingale in our martingale we will consider every edge sampling as a different observation. For every sampling, our edge sample is exactly, so you're sampling the edge E. What does it look like? It looks like the Laplacian of the edge. So that's the matrix that we are adding. And WE is the weight of the edge, the true weight of the edge, and 1 over PE, where PE is the probability of including the edge. This is our sample, this is our edge sample at every step in the martingale. Right? And if you don't sample the edge, it's just 0. Right? But actually, a small difference here is that we need to actually consider mean 0 variables. So I'm going to consider, instead of YE, I'm going to consider YE minus expectation YE. These are our mean 0 samples at every step of the sampling. Good. Is the setting clear so far? Okay. So firstly, about norm control. So about controlling the norms of these samples, we need to say that we need to control the spectral norm of these normalized matrices XE, but we'll actually just ensure that the spectral norm of YE, our edge samples, is bounded by R, where R is something small, roughly epsilon squared over log squared. So once you ensure that norm of YE is small, that implies that the norm of XE is small, because the expectation of YE is a PSG matrix. Okay, so assuming this, let's assume that we are able to control the norm somehow. I will show you how to do that later. Let's first see that the variance of this martingale is bounded. So let's compute that. So the variance of each sample XE, which is just our expectation of YE squared, our expectation YE squared minus the expectation squared. So that's upper bounded by our expectation of the sample squared. But since each sample is bounded in norm by R, we can bound it by R times our expectation. Okay, so for each sample XE, we can bound its variance in terms of its the expectation of the edge samples. But remember, what was a key property we wanted was that when you actually eliminate a variable, the sums of these expectations have to look like the clique. Right? That was a requirement for actually just having a matrix martingale. We wanted that when you eliminate a variable V, if you take the sum of all the edges you sample in expectation, you should get back exactly the clique. Right? So we know what this expectation looks like. It looks like the clique on the neighbors of V. But the clique on the neighbors of V actually is spectrally bounded in terms of the star on incident on V. Why is that? That's because when we actually did Cholesky factorization, eliminating the variable V, you wrote the star on V as a rank 1 term plus the clique on its neighbors. Right? So this means what? Okay, so to summarize, what that means is if you sum over all edge samples that you draw when you eliminate a vertex V, in expectation, you are bounded by the star that was incident at the vertex V before the elimination. Right? But now is the key point. Now we chose this vertex V uniformly at random from all the vertices. Since we chose it at random, we should take average over the remaining vertices. But averaging over the remaining vertices, the average of the stars looks exactly like your original graph divided by the number of remaining vertices. Right? When you sum up all the stars, you get twice the original graph because every edge gets counted twice. And you get 1 over the number of remaining vertices. Right? And assuming, excuse me, okay, can you please not make the noise? I'm on the talk. Yeah, sorry. I hope there's not much noise here. Sorry about that. So assuming the algorithm has fared well so far, it actually looks like the original Laplacians up to a small constant. Right? And the original Laplacian is basically identity because we multiply like in the normalized setting. So now if you add up our variance over all steps of elimination, what we get is exactly the harmonic series. So you get R, a small constant, and sum over 1 over the number of remaining variables. That gives you a log n. So you get 4R log n times identity as your total variance of the martingale. Good. So assuming that each sample has a small norm, which I have not yet shown you how to ensure, our martingale actually has small variance. Right? So the only step now that remains to show is that how do we actually ensure that each sample has a small norm. Excellent. So that's our final part of the algorithm. How are we going to ensure that whenever you sample each edge, each sample norm is bounded by R, where we will require R to be roughly like epsilon squared by log squared. Good. So equivalently, what we want is that the weight of the edge times the Laplacian of the edge upon the probability of sampling is bounded by R. And which means it suffices for us to pick the probability of sampling to be 1 over R times any upper bound on the norm of WER LE, right, in the normalized sense. If I pick probabilities that are at least this large, then a norm condition will be guaranteed. Good. So here's the easy case. Suppose an edge, we wanted to bound this for an edge E that was an original edge. It was already in the original graph. Then we know that the Laplacian of the original graph had one of its terms as WELE. So WELE is actually smaller than the original Laplacian. And that's also true in the normalized sense, which means that the norm of, for any original edge E, the norm of WELE is bounded by 1. Right? And okay, so I said we would like to actually ensure that it's smaller than epsilon squared by log squared rather than just 1. But that's also easy. So for every original edge, you can divide it into 100 edges with weight 1 over 100, and then each of them has norm 1 over 100. So by dividing original edges, you can ensure that for original edges, our norms are bounded by 1. Right? So the only challenge remains is that how do you bound this for edges that are created by elimination? So suppose we were eliminating a vertex V, and it had edges E1, E2, E3, E4. Then in fact, then you would be creating these edges between all these pairs. So you'll create an edge E12, E13, E14, so on. And we want to bound the norms for these edges. For these edges, we are going to use what is called the triangle inequality for effective resistances. What that says is that the norm of the Laplacian of 1, 2 is smaller than the norm of Laplacian of 1 plus the norm of Laplacian for 2. And these norms are again, so these are red variables. So these are norms are in the normalized, in the sense, in the isotropic sense. And a key point here is that this inequality does not require your edges to exist in the original graph. It just requires these edges to form a triangle, right? Which is true because E1 is an edge from V to 1, E2 is an edge from V to 2, and E1, 2 is the edge between 1, 2. So they form a triangle. And whenever you form a triangle, you have this triangle inequality. Okay? But these are really trivial bounds, right? I've not used anything interesting so far. Like I've just said, the original edges have bounded norm, and then you can use a triangle inequality. So what good are these bounds? And really to recognize the importance of these bounds is that they really affect our running time. So we said we are going to pick PE to be proportional to our upper bounds on these norms. So, and the number of expected non-zero edges we maintain in the graph is sum of PE. So if your norm bounds blow up, then our graph will no longer be sparse, and our running time will grow, and we'll not get a nearly linear time algorithm. So we really need to maintain excellent bounds on these norms. Okay, so but let's see, why are these trivial bounds already good enough? So when you eliminate a vertex V and create an edge 1, 2, it gets a weight W12, which is exactly W1, W2 divided by capital W, which is the sum of all the weights incident. Now, if I take this W12 and multiply a triangle inequality, so I've not done anything here. I've just multiplied the triangle inequality I wrote earlier with the weight W12. So that gives me W12, L12, which is the norm I want to bound on the left-hand side. And on the right-hand side, I'm writing it a little carefully. I write it as W2 by capital W times norm of W1, L1, which is a norm I bounded before. And plus W1 by W, norm of W2, L2, which is again a norm I bounded before. Right? So what does this allow you to do? It says that if I maintain these norms, W1, LE1, W2, LE2, then triangle inequality allows you to compute upper bounds on the edges that are created by elimination. Right? And how good are these edges? To see that, how good are these bounds? To see that if we sum up over these bounds, since W2 by W summing over these weights actually gives you 1, adding over all of these bounds gives you exactly the sum of the original bounds. Okay, so if you didn't follow the maths, let me still summarize what I'm reading. So our goal was we wanted bounds on these norms, WE, LE, right? What we did is that we started with trivial initial bounds, where we said that every original edge has norm bounded by 1. So the sum of these norms was, the sum of the bounds that we have was sum M. Now we use the triangle inequality to create norm bounds whenever we eliminate a vertex, right? And we showed that when you eliminate a vertex, the sum of the bounds that you achieve is actually preserved. Exactly. Right? But this sum is also preserved under expectation, because when you sample an edge, like we were preserving the weight in expectation. So you actually preserve the sum of the non-zero norms under expectation. And this means that we are going to preserve the expected sum of estimates. We are going to keep it to be M at all throughout the algorithm. But since the number of edges, the number of non-zero edges we have at any time is given by the sum of these bounds, we are actually going to ensure that throughout the algorithm, we'll only have near linear number of edges in the graph. Okay, so let me summarize this part again. So the last key part of the algorithm remaining was, how do we ensure that sample norms are small? We use two simple facts to bound these norms. We use the trivial fact that an original edge has norm bounded by 1. And then we use triangle inequality to bound the norms for edges you create. And we showed that just these two simple operations mean that throughout the algorithm, your estimates for the norms add up to m. In particular, this implies that the number of edges we have in expectation is bounded by near linear in the number of original edges. And that's it. And this ensures that our algorithm will run in near linear time and will generate a sparse approximate Cholesky factorization with near linear number of non-zero.
Sushant?
Yes.
So how many martingale concentration bounds do you apply simultaneously to the process?
Good. So I didn't actually talk of what martingale concentration to apply. In fact, I was going to do. So we use Friesman inequality. In fact, it's matrix version by Trop, which essentially, like, informally says exactly what I said, that if you have a martingale and each sample is bounded, and your total variance that you expect is also bounded, then you get a Bernstein-like bound on the probability of failure. So, but what this does is that it relates your original martingale to a variance martingale. So this W quantity that I've defined here, which is so you condition on all your previous samples and you look at the expectation of xi squared and you sum this over. So this is the expected variance. So this is also actually a second martingale. And you bound this martingale too. So let me make sure. So here's a proof strategy. We frame it as a martingale. We apply Friedman's. That gives you the martingale on the variance. And you apply Friedman's again. And that basically gives you, allows you to apply a Chernoff bound. And that gives you the proof of concentration. But okay, so here's a different interpretation I think that I have for your question. I think is that, do you need to apply a union bound over all the steps of elimination? Is that the question actually?
Sounds closer, yes.
Okay, sorry. So you don't need to. And in particular, you don't need to do that for martingales. Why is that? So if you're trying to track a martingale and you want to bound that it never fails, right? And that's the right question, because in bounding the variance, I assumed that you had not failed so far, right? So if you want to say that the martingale never fails, you can actually apply the concentration bound to a different martingale, which tracks your original martingale. But if your original martingale fails, then the new martingale just stays there. In particular, it would have failed at the end of the procedure, right? So if I'm sampling a martingale and this is my original martingale, and we are afraid that it will fail and then come back to the success region, right? The new martingale will actually go up, fail, and continue to fail. And you apply the concentration bound to this modified martingale. So you don't have to do a union bound over every step.
So you don't, like in maximal inequalities, you don't have to lose because of this union bound.
Right. But even if you had to do that, you would lose constants. That's about it. Because you do a union bound on a polynomially small probability. Okay. So let me skip the application of the variance part. I do want to say that I cheated a little when computing the variance. You have to do it a little more carefully, and I will direct you to the paper to actually how to get that. So let me conclude. We are basically almost right on time. So what did we show? We've shown that there exists a sparse approximate Cholesky factorization for Laplacians that you can compute in nearly linear time. And this gives you an extremely simple, nearly linear time Laplacian solver. And as I said, that the solver can be actually extended to a larger class of matrices called block diagonally dominant matrices. And those details are in the paper. And I will conclude with that. Thank you.
Thank you, Sushant. Any questions? Maybe you could, one quick question, maybe you could point us to the place where you use the fact that you have a Laplacian as opposed to PSD matrix.
Oh, excellent, good. So in fact, it's used really everywhere, right? So even when defining the algorithm, just think of how do we draw the samples. When we draw the samples, we ensure that whatever you output will actually look like a Laplacian, because we sample edges. We don't sample the entries in the matrix. So in particular, it looks like a Laplacian, it looks like a PSD matrix. And that's not even true. Like if it was a general PSD matrix and you eliminate a variable, then you don't have any factorization to work with, where to ensure that it's a PSD matrix or to stay in that class.
So this is, and this is something, what is known about that? About
PSD matrices?
Yeah, doing it for PSD matrices?
No, nothing is known about about approximate Cholesky factorization. Nothing is known. In particular, it's not known that like what are the conditions under which you can have sparse approximate factorizations.
Another question about the use of randomization. Is this something you can de-randomize?
Oh, that's a good question. So, for example, in our proof, I used the okay. So there are there are two kinds of randomization, right? One is how do you sample edges, and two is the randomization over vertices. So the randomization over vertices, we are reasonably confident is not required, but our proof definitely requires it. We don't know how to control it, but we believe it's not required.
I'm trying to avoid choosing the vertex with the largest degree. Is that the thing?
So in fact, that's interesting, right? So that's how you would try to go about proving, oh, maybe you actually do need some kind of randomization. In particular, you could try to consider a star where you have a vertex with very high degree, and maybe argue that if you pick the star at first, you would fail. But that can't be true, because that happens with probability 1 over n, and our failure probability is polynomially small. So we really think that but that's certainly natural. That say that pick something that's let's say at most twice the average degree, and go on, and that should work. So we believe that works. On the other hand, for sampling, you can there is maybe some hope that you could try to sample the edges instead of randomly as an expander. The challenge there, though, is that remember that I'd said that you have to control the sample norms and sample approximation when normalized by the final Laplacian, by the Laplacian you're trying to approximate. And that's sort of different from the expanders. Expanders say that the Laplacian of the expander you are going to add looks like the Laplacian of the clique you would have added otherwise. But that's not what we want. The normalization is different. So there is hope, but it's not clear exactly how. And even if you could, the parameters are actually worse than what you get by randomization.
That sounds suspiciously close to the original setting, right? We want to approximate a graph by an expander. It doesn't make sense. Or is it?
No, can you say that again?
So this, I mean, potentially this could, if you could construct an expander, also the analysis would become simpler, right? Because
yes,
yeah.
Yes.
Thanks. So any other questions?
Yeah, Sushant, you were mentioning you need to use Friedman's inequality, so you also have to do something with this variance martingale.
Right.
And I mean, did you tell us? Is it sort of deterministically control how bad this variance martingale gets, or do you have to
good.
do more
No.
analysis?
So okay, so if you wanted to do it precisely, here's how we would do it. So you would actually split up. So every edge sample was one observation, right? You would also dissociate the choice of the random vertex as an independent observation in the martingale. Okay, so there is a step in the martingale where you choose which vertex to eliminate, but you don't change the matrix at all.
Okay.
Right. So now you look at in this martingale, everything is norm bounded. That's fine. So now you can apply Friedman, so it suffices to control the variance. Okay. So, but what does the variance look like? So the variance for eliminating a single vertex, you can add all of those variances together. They are for one, they are independent and they look like exactly the clique. So you add all of them. So the martingale you need to control looks like: pick a random vertex, look at its clique, and take that as the first term. Pick a second random vertex, look at its clique, take that as a second term, and so on.
Okay.
Okay. And this one, it's still a martingale. It's not deterministic, but it's again norm controlled because each clique is smaller than the current Laplacian, which, if you're good so far, looks like the original Laplacian. And in average, the clique is small because the clique is bounded by the star, which is bounded by the Laplacian over number of vertices. So you do need to apply a Friedman there again. And actually another Chernoff after that too. Like you get deterministic variances after that.
I see. Okay, you get deterministic. Cool, thanks.
Great. Any more questions? Yeah, I'm sorry. Like this is my first time doing this, and I realize it's a lot harder to find the right places to stop and have people ask.
This was excellent. Yeah, thanks. This was very good. So I'll give that a second for more questions. If not, again, thank you. Thanks for the great talk. And I'll just remind everyone that in 2 weeks we'll have a Swastiko party here, and everyone's welcome to stay. I'll just take it offline. I'll turn off the broadcast. And again, thanks.